This might have resonance.
I was lost in floods, in the fields the birds are singing. I was lost in floods, and the day was just beginning. I just stood there in the morning rain. I had a feeling I can't explain. I was lost in floods, in the
Sat nav, how does GPS work? Well, sat nav cannot work without GPS. Not now. There may be a development in probably 10 years' time where the satellites are redundant, but that's a long way off. Fanfare for the common man, because the common man designed and built it and got it all working. Well, where does it all start? Well, so right from the dawn of man, we've been looking to find where we are and establish ourselves where we are on the planet. That's been fundamental in our survival, and it's still prevalent today. Well, the wreck of the association brought it all into focus. Those who may be familiar with some sailing stories, the Sir Cloudesley Shovel and his fleet were approaching the western approaches, having been wherever they've been, and they, in those days, there was no real navigation techniques apart from the sun, well, a sort of a crude compass. And they were heading towards the western approaches, towards the southwest of England. And there was a crewmate, a crewman, sailor, whose hobby was, days and months at sea of trying to establish where he was. And he realised, he said, well, if we carry on this course, we're going to founder. So he went up to the officers and said, look, I think we are heading for the Scillies. And they said, who are you to override or to think you can do better than our officers? And they accused him of mutiny and actually hung him. However, they didn't take any notice, and indeed the whole fleet was wrecked. 1,400 to 1,800 men were lost, and the whole fleet of a ship, about 3 got away of about a dozen ships. Sir Cloudesley Shovel died as a result of it, and many of the crewmen. So it was the biggest naval disaster that had ever happened, even to this day, British naval disaster. And that prompted the Board of Longitude, where a prize of 20,000 in those days was a lot of money, who could offer to anyone who could give us longitude within 30 miles of their ships when they're plying the oceans. Several rose to the incentive. The most successful, of course, was John Harrison, which you may have heard of. If you've been to the museum, Maritime Museum and Greenwich, all these clocks are there on display. There were several methods tried to be used, and the like the moons of Jupiter and everything, which, okay, but Harrison's had worked out that you could use a very accurate timepiece and get your local noon, which is when the sun is at the peak of its arc, get a time, and that will tell you where you are on longitude. Latitude is fairly easy. You just take your sight of the sun at noon and you can derive latitude from that. But longitude, going around east to west, is a lot more difficult, and continued to be so. So that principle was actually adopted, but it meant taking a sun sight with respect to the horizon or the angle and the time. So therefore you needed a very, very accurate clock, purely to get position, to establish where you are, not where you were going, but once you know where you are, you can then work out where you want to go. So the clock was required to take a sun sight using a sextant, as we see there, preventing wrecks, because there were lots of wrecks. I mean, prior to this, the ships used to tack across the Atlantic. Hopefully they'll end up in the western approaches and Britain. So what it required was a timepiece. That is actually a picture of H4, which is the one which was taken by Captain Cook and many of the naval officers. But Captain Cook, when he was given this to take round on his journeys, he wouldn't give it back because it works. But you need a sextant, you need the horizon to measure your angle. And you plot then, when you've derived your position, now it requires quite a bit of calculation, and you may have heard of the almanacs that you can buy, and you probably still can, but sat-nav is sort of making them a bit obsolete now. You can then derive from these angles and the time of day, and you can derive your position, and you'll derive your longitude and latitude. And what do? You have to plot it on a chart to actually say, this is where I am. Okay, in the middle of the ocean, it might just be on a piece of paper because there's no islands or land around. But nevertheless, you had to plot it using such instruments as this so you can then calculate your position, and you can calculate what you have to do to achieve your objective, your destination. Before we go into satellites, but what is navigation now that we've got a position, and to navigate we have to have where we know where we're going and so forth. And what is navigation? Well, it's the art of travel. And I'm sure probably when you're driving you think, I can do a better way than that. Well, that's the skill. And some people think they're very good at it and some people not. But nevertheless, it is the art of travel. We have to know where we are at all times. We have to know the direction which we want to go and avoid things on the way. And these are called waypoints, and they are obstacles or places of interest. You might wish to go from here to Newcastle, but you want to pull in York or something. But that is a waypoint on your way, and your sat-nav, as we come to later, has that facility to be able to put in a waypoint, or indeed to avoid railway bridges and so forth and so on. So navigation requires position at all times for accurate and safe navigation. If this is known, it becomes, again, it's this skill of actually navigating safely and efficiently. Okay, we all navigate, but we've all done it where we've gone about 50 miles when we could have done it in 10. So that was not an efficient way of navigation. Yeah. So what happens when the sun doesn't shine? You can't get a fix on the sun. You can't see the horizon possibly. So there's got to be something else. And during the 20th century, the use of radio, when radio came into prominence, became an obvious way to overcome the limitations imposed by by not having a clear view of the sun. Many methods, and I'll just give you some which mainly developed during times of conflict, in other words, World War II. A bit in World War One, but mainly in World War II. There was a huge amount of system because there were more pilots in the aircraft lost through not getting home than were lost in conflict. But that's not broadcast very often. Some 20th century methods for deriving position on the surface of the planet by radio techniques. G, just at the beginning of the war. Bernard, the Luftwaffe had to have their equivalent. Son, again a German system, developed for World War II. Lorenz, another German navigation system. World War I, that was. Loran, still in existence, developed by the USA with the UK for long-range navigation, and Loran is still operational and actually still viable. Maybe something on that later. Alpha, a Russian system, and Chaika, a Russian system. It's a counterparty. The Russians had to have an equivalent to Loran, and they had Chaika. And then there's Omega, the first long-range global navigation system. It's a very long wave radio navigation system, which the propagation will go around the world. And if you can listen to the signals, you can derive your position to about a mile. It has been discontinued now because of GPS. Console, it's a system, it's a beacons transmitting pulses. I've actually used Console when I was a young boy sailing out in the North Sea. I've actually used Console, and you can listen to you have a directional antenna, and when the two intersect, it's quite a long process, it can give you a position, again, to about a mile.
That is by like strength of the signal.
Beg your pardon?
Is it by strength of the signal, you know how far?
Yes, it is. It is, yeah. It was a clever system where you could hear beep, 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 and you can count the dots until you didn't get the dot, and so you say you got 6. And you could plot that 6 on one chart and then 7 from another, and where it intersected was your rough position to about a mile. Decca, of course, was developed post-World War II based on the G system, and that was in use. It's very similar in the way it works to Loran, but Decca didn't survive, and it was discontinued about 20 years ago. There were lots of Decca antennas around, transmitting around the coast, and there was one not too far from here, but that was just been dismantled in the last 15 years. And radar, of course, if you have 2 intersecting target beams, you can actually establish where you are using that, using radar. And VOR aircraft is still in use today, and aircraft use it for their positioning. And after that, it's called dead reckoning. Now, dead reckoning means I know where I am now. I've got a position. I'm going to go in that direction. I've got to know my compass bearing, and I've got to know the distance I've traveled. Both of those are open to error. So dead reckoning is a way, we all do it, subconsciously or consciously, because I've walked 50 yards, I've got to turn right now. And that's dead reckoning. But of course, it's open to error. You can make a mistake. You don't actually know which direction you're going in, and so forth and so on. But with artificial satellites, now we can bring into another domain. It can be an alternative to celestial or radio position fixing. Now, with GPS, that is now known as GNSS because there are so many systems up there. This is just 4, and there's probably another 2 or 3 more, which I've not listed here. GPS was the first, which first 24-hour, 24/7 system. There was a predecessor to this. I'll come to that in a moment. But now, in operation, we have GPS. GLONASS came very shortly behind it, which is the Russian system, to actually compete with GPS. Then came Beidou, which is the Chinese system. And then of recently, Galileo, which we're all familiar with what went on in Europe. So there are the four systems which are common now, but there are others. But so what is sat-nav? Well, first of all, you need a positioning package. However you do it, you've got to know where you are fundamentally. Without that, you're lost. As a positioning package, and it listens to the satellites, which I'll come to later, of establishing where we are. Once you've established where we are, we can then have another package, which is a mathematical package, a computer, call it what you will, which then says, if you program in, I want to go from here to, let's say I'm out at sea, I want to go from the Isle of Wight to Portland Bill, how do I do it? And you program it into those who have been at sea and they use the marine navigation receiver. That is a familiar sort of display. And you've got the mathematics to do that. And it does it dynamically. In other words, every time your position changes, it gives you a new course to steer and a new direction, and a new direction to go. And an in-car sat-nav is exactly the same, except it's presented to you differently. It's a map system, whereas on a marine navigation, it can be a chart system, or it can just be latitude and longitude, even without the charts. A sat-nav needs to give you a bit more. But basically, they're the same. Please note, your sat-nav does not transmit to the satellite. So it's a misnomer. People think, oh, I'm talking to them. No, you're not. You're just listening. You're like you listening to Radio 4. You're not talking to the BBC. It's the same. Where did it all begin? That we could actually use satellites for positioning. It all began in '57 during the International Physical Year, when Russia stole the lead. And we're all old enough, well, some of us are, to remember Sputnik. Sputnik went up in '57 and it just shattered the world, you know, they say, whoa, whoa. It was the first artificial satellite to orbit the Earth, Sputnik 1. So began the space race, which we are still in. What's gone across the screen now is about the size of Sputnik. It's just slightly bigger. It's about that big. And all it was a thing to go into space, a sphere with antennas on, and a little bit of electronics which made that bleep, just to say, we're here, we're here. And it worked. It got Russia as the first into space. However, but within days of Sputnik being in orbit, two physicists at the Johns Hopkins University could work out they were able to work out where the satellite was just by listening to those beep, beep, beeps. And what they used, the phenomenon called Doppler shift, as it changed, apparent change of frequency as it went overhead. And that was relation to time and the angle at which it came. You could then establish where that satellite was. And of course, in just one pass, just like that, we know where it is. And they could, I mean, if they could have shot it down, they would do, but that was not the point. The whole point was they said, we can do this, and we can establish where that satellite, because we know where we are on the ground, so we can find out where it is by listening to the Doppler shift and looking at time. But they said, then it became classified. Because if the position of the satellite can be known from the ground, turn that on its head. If we know precisely where the satellite is, which is a fairly relatively simple technique in spacecraft, you can listen to the signals and establish where you are on the planet Earth anywhere, which was a very mind-blowing thing in its day, in the early 60s, 50s and 60s. So it was then taken on by the Department of Defense, and a system was derived called transit. By placing satellites in a polar orbit, there were 5 of them. This was my introduction to SatNav. I was designing satellite receivers, listening to transit. And by placing these into a polar orbit, then a position fix could be derived as each satellite passed you over. What they did, they put them in a bird cage, like so, polar orbits. So we had 5 of them. And what happens, you have to appreciate that with the satellites in their orbital planes spread around the planet, it hopefully equal sectors, like sectors of an orange, we, the Earth, rotate underneath them. Those satellites are orbiting in the universe in their own planes. They don't move around with the Earth. We, the Earth, moves around underneath them. So with these satellites, so every part of Earth from the sun has a satellite pass over it at some time. So that's how the system was worked, where the Earth rotated, we could get, and the satellite passed overhead, you could get a fix. Okay, it was only when they passed overhead, for the brief period they did pass overhead. What this meant, the receivers had to lock on and take a measurement of the Doppler shift, and it took about 15 minutes. And together with the time and the data, which was also transmitted, which was actually the position of the satellite, because that was uplinked from the ground control stations, it was that information was used to derive a position fix. Why? This is the reason why. It was the height of the Cold War. You had US and NATO submarines.
We all live in the yellow submarine, yellow submarine, yellow submarine.
But they were big, cumbersome things, probably about the size of that chair, fitted in a submarine. You wouldn't get one on your wrist, that's for sure. And they were classified. And they were classified for a long time, probably 10 years. But there was a lot of lobbying came from the taxpayer in the USA to say, look, can we have this information? And I don't know what administration it was, but they released some codes of the transit system to the civilian community. And transit receivers were then developed by such companies as Redifon and so forth.
What year, where are we up to?
We're looking about the late 60s, early 70s. Early 70s when they started to release the codes, and so transits, but they were only used for highly professional things like oil rig positioning and quasi-military operations. They weren't for the man in the street yet. And this is essentially where I came in mine. But transit was operational from 1960 to 1996. In the 1970s, as I referred to, late 1970s, there were 2 entrepreneurs from around here, a guy called Mike Perry and Stuart Nickel, were working had a company working offshore rig positioning. And they were having to hire sat-navs from Redifon to actually position rigs out at sea. And what they did, to position a rig, you took many passes of satellites and you got plots around, and then you did the mathematical thing, and you refined your position down to within about 10 meters. And so you knew precisely where the rig was. Obviously for wellheads and also for political reasons this was needed. But they were having to hire this, to put to their chaps, hire the equipment to put out to the facilities needed to actually do the rig. And Stuart and Mike said, well, can't we design our own? And they said, well, so they got some boffins from Loughborough University and other guys and some very clever software gurus. And they designed a sat-nav in the late 70s. I joined the company in 1980 with the first of the affordable yacht navigator, which sold for about £1,500. A lot of money in those days, but the yacht industry could afford it, even though it was like you and I, because it was a lifesaver for navigation. Up to then, it was just dead reckoning and a sextant, and a lot of people just couldn't do it. So that's how transit came into the civilian and public domain. But the problem was, in between a fix, you got a satellite with 5 satellites overhead. Approximately, you only got a fix every hour and a half to 2 hours. In between there were no satellites in view until another one came over the pole and went round. Then and only then when it became within from about there to there could you actually hear the signals. Below there, the horizon scatter would distort the signals. So they only came around about every hour and a half. So in between, we had to go to the old way of dead reckoning. And so, right, we've got to fix. But of course, the beauty was of dead reckoning was, yes, it went wrong because of the errors, because we weren't sure which direction we were going in, and we weren't sure what speed we were going at. Sat nav, the next sat fix, put you right. So it was, and you kept putting you right every hour and a half. So it was pretty useful, and they got into most of the commercial shipping, the Royal Navy, all the Navy ships around the world. It was a huge market. And so I got involved with doing some of the interfaces and part of the designs and designing simulators and so forth. But then during that time of that sort of period when transit sat-nav was being sold to the industry, the Americans were working on GPS. Because of what they learned from the transit, they could now apply. Of course, the big disadvantage is you have to dead reckon in between. What you need is what's called a dynamic positioning system, which gives you a position now. So precisely as you every second at least, if not 10 times a second, you've got to know you wanted that. So GPS was designed to do just that, to give you 24/7. Totally global, worldwide positioning anywhere on the planet, and that's what it does. Then, so after transit, GPS came, and it was launched in the mid-80s, late 80s, and by 1995, it was declared fully operational. Transit only gave you 2D, latitude and longitude. GPS gave you 3D, could tell you your altitude. Okay, not that important at sea, but other places like aircraft and so, it will give you your height above sea level. And it gave almost 3D positioning in the early 80s, as I said, and they put 1 or 2 satellites up just to do the tests, and now there are dozens. But it came fully operational by 1995. As a result, 5 years later, they switched transit off. And I was there when they switched it off, and I was listening to that, it all died. Right now, it was dead. With GPS, this is an old picture because they've improved it. With over 24, there's over 36 GPS satellites up now already. And those There are a lot more than that, and they just park them in orbit in case one of the others goes wrong, out of service, and they just bring it in. And so they've always got plenty of satellites for redundancy. But basically, again, they're in their own orbital planes, and they've got 6 orbital planes around the planet. They're not geostationary, no. They are orbiting. They're at a lot higher. They're at 20,000 kilometers. So their period time is about 12 hours to go around. But there's always 3. You need a minimum of 3, which I'll come to later. You need a minimum. There's always a minimum of 3 satellites. It has to be visible for you to derive a position fix. 4 to give you altitude. But nevertheless, that's how the system works. So, but that's just GPS. Now the manufacturers designed their receivers to listen to GPS. Now they're designing it to listen to GLONASS, to Galileo, and to Beidou, so it can listen to any of these satellites. So if there's 30 of each system, there's at least 100 satellites they can listen to, and they do. So rather than call it GPS, which was peculiar to the American system, it is now referred to as GNSS, Global Navigation and Satellite System. And it gives continuous 3D position all the time. But accuracy starts to come in now. How accurate are they? This was the first commercial GPS receiver designed and built in Daventry, which is where I used to work. And it was about that big, reminded of a shoebox. It was solid. There was a cast aluminium case. And that got itself everywhere. There's even one of those on the Royal Yacht Britannia. If you see, you can go into the bridge and there's one of those. I've got one. It still sort of works, but it's a bit slow. But that was the very first one, commercial satellite GPS system, satellite receiver, that Polytechnic called Navstar. They changed their name to Navstar, called the XR4, and that was the very first one that came out. That was in the early 80s. Are we okay? Do you really now want to know how it works? Are you happy?
No, I'm not the first person to want to hang the person.
I'm sorry?
I'm not the first person to want to hang the person.
No. It's a lovely anecdote, that. How does GPS...
Is it true?
Well, it may be an urban myth, but it is reported. I mean, they hung sailors for mutiny at any time. It was not quite the same as it is now. Let you out for good behaviour. No, if you did something wrong, there's on less mouth to feed, wasn't it? So how does GPS work? Well, you've got all these satellites orbiting the planet, and we the planet are rotating underneath. The principles are the same. We rotate under these, and as one satellite goes out of view, there's always another one coming into view. What is GPS? It's an old display. This, it stands for Global Positioning System. Again, it was the Americans who coined that at the time. There are 3 parts of GPS: satellites, the receivers, and the clever software that does it. Obviously, the receivers and the satellites are all intertwined with software. As we know, we're fully aware there are thousands of satellites around the planet now. Okay, but it's a big area up there, but there are literally thousands, if not 10,000 satellites. But GNSS satellites are solely dedicated for navigation and timing, which I'll come to later. That's their sole purpose in life, for navigation, positioning, and timing. Consists of at least 24 satellites. Again, we've got about 36 in operation now, and they're continuously transmitting signals. So each satellite comes over your place about twice a day, continuously emitting signals. So that ground-based receivers on the ground can actually receive their signals, and if they're in obscure places, they can get signals from one to another and so forth. There are always plenty to see nowadays. And so they can establish where they are anywhere on the planet. Each satellite transmits data of its own location as it flies along, transmitting data. It's the digital world. It has been for years. It's just an encoded digital signal. It's complex. A lot of it is classified, so you need encryption and so forth. Some of the codes have been released to the civilian community. It's the same scenario again as transit. They let some of the information to the Joe Blogs on the street, in other words, the civilian community. There's a lot they don't. So, there's another strata of classified information. And how GPS work, they use a bit of Doppler information, but mainly it's the time that it takes for the signal from the satellite to land into your antenna, the actual time. And that is used, and as you can see several satellites, you actually measure the time from each of the satellites that it arrives at your antenna. And by working out the time, you can work out the distance away that particular satellite is from you. Velocity times time, velocity is the speed of light, times time can tell you the distance. So we have a very simple arithmetic here. If it took 0.06 seconds to receive the signal, and they measure that by synchronized clocks, you can tell exactly how far that satellite is away from you. So say we do it in your head. That's the speed of light, either miles per second or kilometers per hour. This particular example, that satellite is 18,000 kilometers away from you. Now they can measure the time down to microseconds, so you can get a very accurate timing. And the way they do that is each satellite, each GPS or GNS satellite, has a clock on board, a master clock, which is synchronized, and all of them are synchronized together by communication link. So it transmits a time signal, which is what we know is a reference to the satellite time and converted to UTC, which used to be GMT. However, it's the actual time. And because as the signals come to the ground receivers can actually lock on and do what's called a phase lock loop and lock their own clocks in your GPS receiver to that of the satellite. So they've got a precise time reference. And with using that, as the signal is transmitted, it's got a timestamp. By the time it gets there, it's been delayed because it takes a while for, not very long, but a while for the satellite, like 0.06 of a second, to get to your receiver. And you can actually then measure that, and you can derive the actual distance from here. Let us say that light is a satellite. From here to that satellite, the exact distance to within meters. So so you can do that with one. You can do it with all of them. So if you can do it with one, now we come to the fact you need more than one satellite. You're somewhere, if you measure the distance and the actual plotted distances have got a radius of, that's irrelevant actually. But somewhere you're on that circle. You don't really know. You can be anywhere on that circle because that's what the time calculation gives you. but that's not much use to you. If you have 2 satellites and you have this calculation, you can either be there or there. Again, ambiguous. So therefore, you need at least 3. So if you measure to 3 satellites, that one has got a radius of that one's got a radius of that. It can only be there. You can only be there. And now multiply that up. Say you can listen to 20 satellites. You've got all these circles. That error will go smaller and smaller and smaller. So you actually have 3 satellites. You need a minimum of 3 to give you your position. That's why it's not a problem nowadays. It used to be when there were only about 6 up there. But you can. There's plenty now. So before you go too far, everything has got to be precise. So therefore, you've got a master control station which is monitoring the satellites, listening to the satellites, monitoring, and it does an uplink to actually transmit any corrections. It's listening. Are you in the right position? Or we think you are slightly different. We're going to slightly different to what you say you are. We're going to correct you. So all the time they're being corrected from the ground stations. Well, it isn't all the time actually, because they are pretty reliable. And when they start to see an error building up, they say, "Oh, do an insertion and control it." But they're not free flying. They're actually controlled from the ground. And then the resultant is that then you, the user segment, sat nav, yachting, or in your mobile phone, can listen to those satellites and derive your position on the planet. So that's what's behind it all. You never see that, but that's what's happening. Now, to get accuracy required for sat nav, you've got to be pretty good. So, what are the likely causes of error? I won't go too deeply into this, but if you think about how light travels, is how light radio waves travel, in other words, satellite signals travel. We've all seen the pencil in a glass of water. It appears to bend, called refraction. As the satellites transmit their signal, I don't know if you can see this, as it goes to the ionosphere and troposphere, the signals are slightly bent and refracted. That can cause a timing problem because they've gone a longer distance than they really are. So that can give you an error, and that happens to all of them. So you start to get an error box. We are in with here somewhere, and that error box used to be about 100 meters, which is not good enough for sat nav. We'll come to that again later. So that's a cause of error or dilution of position, and it can degrade it so that it used to be 100 meters. Now with umpteen satellites, we're down to about 10 to 15 meters open-ended accuracy, which is slightly bigger than this room. Again, not suitable for sat nav in your car, but you can be the other side of the road, can't you? So they have to do a system to increase the accuracy, and they have a system called differential correction, where the errors due to the satellite and propagation and so forth are a fact. We can't change the troposphere, we can't change the bending of the signal. And of course, that's subjective to how the sun is feeling today and whether it's moving the atmosphere, the troposphere and the ionosphere about and changing the bending and everything. So therefore that's out of our control. So we get this resultant error, and we have to do something about it. And we can do something about it, very clever, called differential correction. If I know precisely on the planet by lots of other survey techniques, which exists, but you use the celestial positioning. Also, but we've got plenty of time to do that. I know precisely where that bottle is, and then I've got, let's say, a sat nav, and you put it on that position. It might say, "Well, I think you're there," but it's an error. That's a wrong. And then next second, it might think you're there, and so forth. There. So therefore, there's this constant error when it's exactly, we know where it is. So they use that error to say, right, at this moment in time, the error is southeast 50 meters or 30 meters. And they send that error signal out to your GPS receiver. It's all done automatically, don't worry. And your GPS will say, okay, I'll take minus 30 meters in this direction. I'm here now. That's called differential correction. Problem is, how do you get that information to your sat nav, to your GPS in your phone, on your boat? Where? How do you get it? In the olden days, there used to be a service set up. I think Fugaro was one of them, who used to do the differential correction and transmit it on another radio signal, and you used to have to buy the service so you could get differential corrections by a radio link. And they used that for a long time, again on rig positioning out at sea. When it was the professional boys, the commercial boys, it was worth paying for that. But Joe Bloggs in the street on his yacht couldn't afford such a system because it was expensive. So then they came up with a very clever system called SBAS. What? Okay. We have the reference station, which we know generates the error. We uplink that error signal, which I've just described here, up to a geostationary satellite, or even a TV satellite, and it's retransmitted down to us, the user. What it does, it very cleverly, it transmits on exactly the same frequency as GPS. So your GPS receiver says, oh, I've got another satellite here. Oh, no, I'm not. It's my direct, because there's a code in the signals. Oh, no, it's not. It's my corrections. Therefore, I'll use these corrections, and you refine your position. Suddenly, when it's open loop, without this correction, it goes from there, goes to there. And when you first switch a GPS receiver on, you can actually see that happen. It's not got SBAS yet, because they all receive back, nearly all of them receive SBAS now, and they use it for correction. By so doing, what was the 10 or 15 meter error has now gone down to about 1 or 2 or even sub-meter accuracy. Now we can use that, can't we? So it's called SBAS, satellite-based augmented system, and that's the principle of how it works. And the service satellites, which are not the GPS satellites, the Inmarsat or the TV satellite, cover certain areas. So and they're referred to as WAAS over the United States, EGNOS over Europe. We're coming back to WAAS again, over to the north part of Russia. MSAS over Japan, Gagan over India, and this is old. There are more sites available now. So wherever we are now, we can receive our correction signals. If we now, by definition, have corrected our signal, we are now accurate to about 1 or 2 meters. We can use that very accurately. You may remember this from the coronation. All by drones, position and location over London by GPS. Very clever. So that's how, and they're on station. And I was talking to a guy, there's actually a guy, a company in Daventry do all this. I was talking to a guy there, and they said they only let one guy control them. Because to get two people, they'll get confused. They only got one guy to control this lot. Okay, it's a computer program, but if one goes sick, they have spares up there, spare drones. If one goes sick, they bring another one in. And again, it's all software driven. But
It's impressive they stay there.
sorry.
They stay there even with wind.
Yeah, because they can do 3D control with these, with the batteries and the little drones. So yeah, so that's how GNS now enables super accuracy. They're probably on the station to within the area of that size of that table. So, in a nutshell, how does it work? Position is calculated by triangulation. In other words, distances from the satellite. The distance is measuring how long the signal takes to get from the satellite to you, and it does that for every satellite in view. Therefore, refining your position down to an error box, a small area that you're in there somewhere, probably. And now by SBAS, we can be essentially within a meter. So, what do you do with it? In the good old days, and still, we used to use latitude and longitude. And any sailors here would be fully familiar with latitude and measuring north, south, and east, west, and longitude, east, west. Sea and air navigation uses lat long. However, for in-vehicles, most people wouldn't, the majority of people don't know what lat long is, disrespect, but they don't. So, and they can't use it because you've got to plot it. So it has to be done for you. So, but before that, we need something to portray this information to you. A set of numbers like latitude, X, Y, Z, and longitude doesn't mean an instant thing. You have to relate it. So it's not much use. But with modern electronics, we have now gone to electronic chart display systems, which came in 20, 30 years ago. And now every ship has one of these. It's part of a TV screen, just like this is of your chart, okay? And they just digitized, originally they just digitized the Admiralty charts. And so they knew it was digitized, they knew the latitude and longitude coordinates. And then you could plot your position from your sat nav on your boat onto a chart, such as I'm here, you can be going up this channel, you want to go up this channel because that's the deepest, you don't really want to hit that. So your safe navigation techniques start coming down. You've got a chart to know where you and show you where you are. That was for the marine world. Well, we can do the same for the land world, if you like. A sat-nav display. We've all seen them, but they have to be simplified. But so you can expand, as you know, you can expand or contract your chart display. Maps are also part of a sat-nav system. How did they get the maps? Believe it or not, by these methods. They sent a car around with a camera and differentially corrected precision GPS receivers around virtually every road in the country. Why? Because they tried to get the information from the Ordnance Survey, and this is many years ago, and Ordnance Survey did not realise or recognise that this could be valuable. And they said, oh, we want to charge you £1,000 or whatever. So they said, nah, we'll do it ourselves. And they fitted up cars with this to travel every route. And they didn't have to stop, they just go along plotting. And so they had cameras. Oh, there's a hospital there, there's a pub there. They put all that into the database. And there'd be a guy there just annotating as they went along. Police station there, crossroads there, that's a one-way street, can't go there, and so forth and so on. By that. And when you couldn't get on a road, they used a guy on a backpack walking the pathways not just this country, virtually every country in the world. Probably some parts of Africa that have not done it, or South America. But nevertheless, the civilized world, I should say that, has had their map of the planet in a database. There was a furore when Google Earth was coming around your street with its camera looking at all your houses. And we probably all use them now. You can actually have a street view of your house or whatever. Except that is the same principle of what they're doing, taking all the data. They then amalgamate together and make an electronic map for you. Towns, cities, villages, as I said, everything was gathered from driving or walking the data loggers. Yes, they do have a go at Ordnance Survey, Phillips, etc. But there's always the copyright issue, and that's a thing they don't really want to go into. So that's why, and the way they don't use that too much. But the two big suppliers are a company called Navtech. They've got an office in Holland, and Google, of course. Google's everywhere. But they are the two big map suppliers to the sat-navs you have in your car. Waypoints are locations or landmarks which can be... Right, you're going along a road, you've got to turn left at this to get to where you want. That is a waypoint, and they are stored in your route. We know whether it's a one-way street, we know the sort of street. All this data is in there, huge amount of data. It's all in your sat-nav, and a host of many features which you see and you just take for granted. And you plotted in where you want to go to, and your sat-nav will calculate by its navigation package how to get there using the map database. And how does it do it? Well, how does it know to go that way? Funny enough, in 1959, there was a mathematician called Dijkstra, who was having to take his children to school and back. And he thought, well, there's lots of ways to do this. And he said, well, which way do I use? So when he was waiting for his children or child to come out of school, he sat in a cafe. And within an hour, he'd come up with an algorithm to find out which is the best way to take to get from there to there. And he came up with this algorithm. He's a very clever chap. And it's called the Dijkstra shortest path. Oh, and it's used in all your sat-nav. It chooses your shortest route, unless you choose to be different, of get you from A to B. So that's used, it's a standard algorithm which is used to calculate the shortest distance. Furthermore, we have a thing called, although GPS position, as I've said, is accurate to sub-meters, your maps are not always. In fact, they are the biggest error in your system, the maps. So what they do is that you would not appreciate that although your GPS says you're in this field, you don't want to be plotted there. You actually know you're on the road, and your sat-nav knows you're on the road, so it actually snaps you back onto the road, and it's called map matching, and it snaps you back onto the obvious route of where you are. It's cheating, if you like, but it works, and it's called map matching, and it's involved over quite a long time, and it just puts you, it correlates GPS position to the map database it's got. It's called map matching. And the best example of this, I'm sure you've all done it, you've decided on a route, and particularly if you're going down a motorway, it wants you to get off at a exit. And you say, I don't want to do that, I'm going to go straight on. And as you go straight on, your sat-nav then continues to go up the side road, because it assumes you've done it, until it realises it's not there. And then suddenly it's snapped back onto the road. That's the map matching system coming in. It assumes you're going up there, but you've said, no, I'm not. And they say, hang on, this position, all right, I'll put you back on the map. And that's how it does it. You'll notice it next time. You do it with an exercise, but that's what works. So a review. A sat nav and marine navigation are very, very similar. They have a navigation package, they have a positioning package. The display and presentation to the user is different, but horses for courses. In the sat nav in your car that you get obviously been tailored to you, to the driver, to driving and navigation on the country roads, on the roads of the country you're in. But of course, now we've evolved with a lot more information. You've got continuing position from GNSS. You've got navigation from your current location to where you're going, the fundamental reason you're having your sat nav. But then with cellular, it can give you some traffic alerts and tell you. You can map, you'll have the map preloaded from a database. Yeah, we've all had it. Oh, my map's out of date. How can I? And you have to reload another map. You either pay for the service, or you do it on air, or it's automatically done from your mobile phone. Whatever, the maps are constantly needing updating, and there is a process to do this. Either you buy a new disc and pay for it, or you've got a service which automatically updates it. But nevertheless, that maps are dynamic; they're changing all the time. So you seek to get, but the modern sat navs accommodate that, so they get the latest map. And of course, now the synthesized voice, whoever it may be, to tell you what to do. Personally, I'll switch my voice off, but. Right, the major uses of the satellite constellations, apart from deriving your position, they can now be used to derive true north within fractions of a degree by using two antennas and two receivers. Tell you precisely the direction to the center of rotation, the true north, the center of rotation of the planet. Now, the other major use of GNSS is timing. Timing is fundamental to it, and it's used, what's known, or it's now used as universal time coordinated. So simply that means this microsecond here now is exactly the same microsecond in Tokyo. You can't do that by any other way except by phase lock satellites together. So you can now time everything. Telephone exchange packet switching. Have you thought that the number of calls that go across the Atlantic from the UK, just Europe, by cable, there just aren't enough lines, cables, wires under the ocean. So what they do is they listen to when you're talking, and if you have a pause, the timing switches you out to another and switches somebody in, and they multiplex all these conversations or data things, and then they're put together at the other end. We can only do this by precise timing, and that's what's used for telephone exchange packet switching. Frequency and phase control of TV stations. Your DAB radio